Let's take a look at the first example. Determine the accumulated value of annual deposits of $8,000 for 15 years into an account earning 11% compounded quarterly. Here we have an annuity where the deposits are made annually, and that's important to note because the interest period seems to be calculated quarterly. So we have a conflict right away. However, we don't have a conflict if we decide to draw our time diagram. So let's start with a time diagram. We've got 0, 1, 2. How many deposits do we have in 15 years? Well, if they're annual deposits, we'll have 15 deposits of $8,000. The first deposit, we assume, is made at the end of the first year. So there's our $8,000 at the end of the first year, $8,000 at the end of the second year, and so on until the end of the 15th year. We've got 15 annual deposits of $8,000. Let's draw an annuity bus around that to emphasize the fact that we have an annuity of N is equal to 15 deposits. So we'll show that the first payment is made at the end of the first year and the 15th payment is made at the end of the 15th year. We're asked to determine the accumulated value of these deposits. So that means that we need to find the final value of the deposits, and the final value includes all 15 of them plus the accrued interest. The final value is an inflated value. It's going to be a maturity value, so that will be the final value will be the $8,000 per year multiplied by the final value factor for an annuity, and that would be multiplied by 1 plus the interest rate per year for 15 years and 15 deposits, take away 1, divided by the interest rate per year. Now that's very interesting, and you'll note that I used I per year in the annuity factor, and the reason why I did that is because we don't know the interest rate per year. What we have is an interest rate that is compounded quarterly. In fact, what we have is a rate of 11% compounded quarterly, and what we need to do is we need to step aside and convert that to the equivalent annual rate so that it matches up or coincides with our annuity payments. So, in stepping aside and working out the equivalent rate, we start off with 11% compounded quarterly. 11% divided by 4 quarters per year means that we have an interest rate of 2.75%, 2.75% per quarter. And that's important because now we're going to say, how do we get the annual rate that is equivalent to that 2.75% per quarter? Well, we're going to take a 1-year period, and a 1-year period, if it's compounded quarterly, we'll have 4 quarterly periods. So that was good. That means that we'll have 1 plus 0.275% per quarter for 4 quarters, and that's going to equal 1 plus my annual rate, that's the rate per year, for 1 yearly period. So using your calculators, 1 plus 2.75% compounded 4 times will give you a value of 1.11461212, and so on. Leave the entire number on your calculator display, and that's going to equal 1 plus I to the exponent 1, or just 1 plus I. Now we're going to subtract 1, and we end up with 0.11462, and so on, is equal to the interest rate per year. So what I'd like you to do is to store this in one of your memories. Maybe you can hit store 1, and we'll use that as the interest rate. Store that in 1. 11.46% per year is equivalent to 11% compounded quarterly. We also will need 1 plus I as a factor in our annuity formula. So perhaps what we can do is add 1 back to it and store that in memory 2. So store memory 1 for the interest rate and store memory 2 for the 1 plus I factor. Now let's go back to our annuity calculations and substitute those values in to finish off our future value. And so now that we have the equivalent annual interest rate, we can substitute directly into the formula and compute the final value. So the final value is equal to $8,000 per year multiplied by the annuity factor of 1.11462 and so on. Power is positive 15, take away 1, divided by 0.11462 and so on per year. Now we have the interest rates and the payment periods coinciding. With that annuity factor multiplied by $8,000, we're going to end up with a final value equal to an amount of $285,619.01. So the future value includes the deposits plus the accrued interest. And when you're using your calculator to work this out, the annuity factor that is, you know that the 1 plus I value is stored in memory 2. So you can simply do recall memory 2, raised to the y power x to the power of 15, subtract 1, hit the equals bar, then divide by recall 1, that's where the interest rate is stored, and hit the equals bar again. You've got your factor. Take your factor now and multiply by $8,000. Now, if you're using the BA2 Plus calculator, the business financial calculator, you can actually avoid the step for the equivalent interest rate by simply using the built-in functions. So you're going to clear all the registers, hit the PV, press PV is equal to 0, so enter 0 into the present value formula. We've got negative 8,000. Those are the payments. So negative 8,000, press the PMT function or the PMT key. And 15 is the number of payments. It's always the number of payments. So press 15 and N. And now we'll enter in the interest rate for the annuity. And in this case, it's 11. So we'll key in 11 and IY. And then we need to indicate the fact that the interest periods and the payment periods do not coincide. So we'll use second IY and enter in payments per year, PY, is equal to 1. And compounding periods per year, remember to hit the enter key and hit the down arrow button to get into compounding periods per year. That's 4. And enter second quit to get out of this function. And now we are ready to compute the future value. So you can press compute FV and you will get the same final value.